Okay, testing. Okay, thank you very much. Okay, we will resume the lecture, and during the break we have a quite a interesting discussion. Okay, more practical discussion, talking about uh, also related to the silt trap. Okay. Some discussion we're talking about the pressure generated originates from the flushing action. Okay, it could be generated locally at the appliances, and we'll come up with some siphonage action. Or maybe you may thought, okay, if there is a siphonage is a problem, why don't we to arrange no branch pipe? But the point is, we need to consider also the space available for the occupied area, functional needs, and arrangement. Also, we need to consider some economical reasons. We will occupy a lot of spaces if we arrange a lot of stack, get closer to the appliances. So that we need to shoot for the balance. Some appliances will be collected by a stack. Okay, for the long appliances, okay, some distance to the stack, okay, the appliances may be collected by another stack. Okay, therefore it is unavoidable. We need to have the branch pipe. Okay, that's some sort of interesting discussion during the break. Okay, now in here there's a page we're talking about the unventilated and ventilated branch discharge pipes, because as we mentioned, the branch pipe is unavoidable. All right, and this branch pipe arrangement will largely affect the siphonage action. In order to avoid the siphonage, we need to arrange the branch pipe in a special arrangement so that we can avoid the siphonage. Now, the standard design guide provides us some convenience tool to list it in terms of the table or graph, so that the siphonage action will not be occurred. All right, here just to give you some example. This example is comes from the plumbing drainage design guide. Okay, we remember we use the underlying assumption to the set of design parameter. We need to retain all the set of table, because the table is generated from the setting of that parameter selected. Okay, here for the plumbing engineering surface design guide, actually is a system free of the pre-SEN. Okay, now the arrangement here say for the appliances for limitation of unvented branches, which means the branch without ventilation pipe, additional ventilation, there's a length limit in length, okay, and also the gradient limits, okay, cannot be too large, cannot be too small, okay, and also maximum number of bands and vertical drop. Vertical drop means that the pipe to drop and then horizontal run, okay, and that's our limit. Exceeding the limit, which will create a siphonage action, excessive. Okay, so this so-called unvented one, which means, okay, if the pipe can fulfill all the requirements here within the maximum length, okay, the pipe gradient in between 18 to 22 mm per meter run, which means a drop 18 mm per meter run, which is a gradient. Okay, and a maximum number of bands, okay, no bands, no drop. If this is the case, this pipe can be unventilated. Longer than that, we need ventilation. All right. So the table put in there is mainly come from the experimental results. Okay. So list down all this requirement. This one is an example come from the plumbing engineering surface design guide. We got something more from the British standard. Okay. All these design guide have a very strict configuration of the piping layout, such as they will refer to certain something like this. Okay, no job. For this one, can I close this one? Okay, no job. Okay, have a limitation of length. We can consider, okay, we have a limitation of length, no ventilation pipe, the toilet layout will be restricted. If you want to move, okay, one facility to one side to another side, the length will be excessive. Okay, maybe you need a ventilation pipe. Ventilation pipe requires a more space for arrangement. Therefore, for engineer, for us, we need to coordinate, okay, with the user, from the user point of view, from the architects, from your engineering point of view, to make the system works. Also, good fit for some other purposes, such as spatial arrangement, space utilization, ease of maintenance, ease of access, things like that. We need to shoot for the balance, okay? So that I cannot say you have the design project and come up with all the same design. Impossible, okay? Because you have your own preference about the use of the system, okay? All right, here's a several example for the ventilator branch. Same arrangement of the appliances, but the pipe limitation still have the limitation even you have the ventilation, because the ventilation pipe has to be designated with the size. Okay, the size is only can provide certain amount of air, but not too many. So within this limit, you can extend the pipe from the original, say 1.7 meter up to 3 meter, longer a little bit. If longer than that, okay, you need to arrange another the piping layouts, the toilet layouts, or maybe you need to add one more step, for example, if the layout cannot be changed. All right, so then we need to make a judgment. The first column is interesting. The diameter of the branch pipe, this diameter is fixed. Okay, therefore do not apply your calculation or to calculate flow rate for single for a branch pipe connected to a single appliances. Need not, because let's imagine a single facility, single appliances. Once discharged, upon discharge, the flow rate will be fixed, which is the maximum. Okay, the simultaneous flow rate we talking about in the last lecture only occurred at a number of the appliances get connected together. Okay, the flow rate. Okay, the flow rate is due to a number of appliances. Now, at that situation, we are going to consider the simultaneous discharge. Therefore, the simultaneous discharge calculation only, in this case, residential one, at the stack only. Okay, and all the branch pipe, the size are fixed. Good for the maximum flow rate for a single appliance. Right here are the figures referring to the table. Therefore, when you look at the table, find the size, there are some keynotes. The keynotes are referred to the description there, and also refer the definition about the distance, job, and the bands arrangement. So that the figures give us a better illustration. Okay, here's also the example ventilation. Until certain point, here's an unvented part. For the ventilation part, you can extend, okay, for the branch part. Here's the illustration, much more clear for us. And also some come from the experience, come from the utilization example, experimental one, how the pipes will be arranged. Some area are not allowed to joining the pipes, okay, joining the branch pipe in order to avoid the momentum of water, okay, go into the branch pipe. If unavoidable, there's some special fittings for the connection. Okay, here also have some dimensional requirements. Okay, whereas we need to avoid the branch pipe connection to the stack. Okay, some sort of restriction. Okay, for the ventilation pipe connection, here also the limitation requirements, gradient requirements. Okay, and size requirements. If all these requirements are followed, the table are applicable. So that this is my meaning. What I mean is for the entire set of design have to be applied as a bunch. Okay, this bundle. And this set of design, what I call, okay, is so-called a pre-calculated design. This so-called pre-calculated means based on the set of the calculation parameter, which the design guideline provide us some the table, and this table still have some flexibility to arrange our system layout. Okay, even so, this arrangement still gives us some space, okay, and alternatives, so that the pre-calculated design is flexible enough to fit into the typical building layout. All right, here's the purpose of pre-calculated design. Here is the one. All right, here the description for the both. We will not go through one by one. Okay. Now from the insert plumbing design guideline, now we jump to the BSEN. For the BSEN, basically, which try to have a description to the more wider system architecture. Okay, such as for the same arrangement, say the flow rate, okay, capacity, nominal diameter, each will classify it into the different system. System 1, System 2, System 3. Okay, different filling degree if we still remember. So if we follow a set of the design parameter, we need to stick into a particular system to use the pre-calculated design part. Okay, so give you an example. The branch layout, apart from the previous design guide, it will list, say for the system 1, the arrangement is like that, but the dimension will be different. Say the maximum length, calculate from here to here, the maximum system 1, it will be 4 meters, but the system 2 will be 10 meters. Okay, system 4 will be 10 meters, things like that. But the gradient will be different. And all this combination, I refer is a pre-calculated design. And this pre-calculated design, just your application within that limit is workable. All right, the British standard try to handle the problem in that way. Similar arrangement, but try to incorporate for different areas the concept. Okay, similar table. Okay, talking about the appliances. The appliances, okay, the pipe diameter, and also the dimensional requirements for the pre-calculated system for the system 1, system 2, system 3, system 4 as well. So for each of this table, okay, got the layout arrangement, but subject to the different dimensional requirements. One set for unvented pipe, another set for ventilated pipes. All right, so that they presented in this format systematically. Okay. Now we take a look on the another presentation. This one is come from the European tradition. European tradition and applied it to our sister city in Macau, just next to us. And another curve I put in here, I extracted from the earlier days, the experimental data, which this is presented into a graphical format. The graphical format is talking about the branch pipe inclination and the length. Okay, I think in your laboratory there's a quite old-fashioned experimental test rig. Okay, to pump in the water and try to test the siphonage action and how much water seal we retain in the after the discharge. Right now, and this presentation, okay, I shall draw in here. Here is the length of the branch pipe, and the branch pipe arranged with the inclination, which is a gradient. Okay, different gradient and different length will have the different effects about the siphonage. Here is the limit, which means if the length is longer than that or gradient larger than that, we will have a siphonage action. But within the limit, no siphonage will occur. Okay, so that the graph will be like that. Okay? Some standard represents the data in terms of the graph, not necessarily the table. Okay, so then for us, okay, we can use any kind, any design standard, okay, with the fundamentals. This one we have described, which was misplaced as should be in the before. Therefore, we have already discussed it. Okay, now the next slide here is we're talking about the capacity. The capacity means how much water that a stack can be handled. When a stack handling the amount of water, not necessarily talking about the flow capacity, but the flow capacity will associate it with the pressure generation. So that in there, the capacity, we will have a term such as a quarter full flow. Quarter full flow means we don't have a figure for that. Quarter full flow means stack, okay, will not be filled up entirely with water. We allow some air core inside, because once the water flowing into the stack, the water, the effluent will adhere to the wall of the stack and form a so-called annular flow. Okay, and at the center of or section of this stack, which is the air core, and this air core, okay, fill up by 3/4 of air in terms of area, only 1/4 fill up with water, and with this design condition, the limits to quarter full flow, that's an equation whole. This equation is an experimental result come from the Wiley at Ayton 1960s, long time ago. Still too complicated, the equation. We make it simpler. Okay, Q in liter per second, which is the flow capacity, which is allowed flow capacity maximum flow for a vertical stack. Okay, and then K is a constant, okay, collecting all the constant lumps together, and be a single number, single values for quarter full flow. Okay, and then D is the stack diameter. Okay, when we do not have any further information, just use it. Okay, however, for this equation, do not have much information how the branch pipe get connected to the stack. All right, and for the later, some other information, say the pre-calculated system, I extract one more example from the engineering design guide, which okay, here for the design guide here for the stack, which dictates the capacity, full capacity for the different arrangement together with the ventilation arrangement. Say for the primary ventilated stack, 100 pipe is 5.2 liters per second. The 5.2 liters per second will be calculated by the same design guide methods as well. If we've got the secondary ventilation, which means the pressure can be mitigated by additional air introduced to the system, so that we can allow more flow rate, not 5.2, but now it's 7.3, more flow rate, which will generate the same level of the pressure. All right, that's the reason why. It doesn't mean, okay, the ventilation pipe can allow the additional flow rate, doesn't mean that, but to introduce the air in order to mitigate the pressure variation. Okay, here is the engineering design guide. I try to describe every slide where the information comes from. And my intention is to illustrate the principle, but not illustrate the design procedure into a single set. The design procedure will be addressed in the later lecture. Okay, the British standard, how this will be handled. Additional information. Okay, now for the general stack capacity, a single stack, we have an equation. Okay, design guide, the Institute of Plumbing design guide, which give us additional information about the ventilation condition. Okay, British standard. Apart from the ventilation condition, in the British standard, give us some more information about the square entry and sheet entry, which the branch pipe, how the branch pipe get connected to the stack. It's just having a very smooth flow into it, which generates less pressure. Once generate less pressure, we can find that the flow capacity is larger, more. Okay, because the less air pressure will be generated. Otherwise, the flow rate, the capacity will be reduced. And this reduced part okay, we can compare the numbers. Okay, 5.2, okay, just approximately equal to the Institute of Plumbing Design Guide. Okay, so we can imagine, okay, it must be street entry, same approximately. Okay, we can try to interpret it that way. Not necessarily 100% correct, but we have, we can have some interpretation about these numbers. Okay, ventilation, secondary ventilation, more ventilation, more the capacity. Same principle. Okay, air admittance valve, which is a misplaced part. But I would like to emphasize this part. For the pre-calculated system, which we have the limitation, okay? And the limitation in all of this pre-calculated system, which may be not fully fitted for our skyscraper application, okay? Because in Hong Kong, you can look around. We have a lot of high-rise building, just the rental space is limited. Therefore, you can see just like a lot of chopstick, okay, put on the rise, bowl of rice, okay. And those of the high-rise building, the height and the arrangement due to the small places may deviate from the design norm imposed to those of the pre-calculated design. Okay, that may cause some problems. From our previous design reports, okay, we have already encountered those of the problem, but not that serious. But once the buildings, okay, got higher, taller and taller, okay, higher location, we encounter problem more frequently. Okay, one of the problems we need to take care in our design is about the ventilation, mainly come from ventilation. Okay, in the British standard, there's a sentence, there's a condition looked at here. So-called stack vents, ventilation stacks or ventilating branch pipes shall be increased in size if they are long or have many bends. Okay, it do not dictate, okay, how the distance is limited and how many bends over there, but to alert us if the arrangement deviates from their pre-calculated design, we need to have the additional consideration. Therefore, I think I have to address this seriously to you for high-rise building, very high-rise building, that the ventilation pipe size, okay, have to be increased. You can look at just some residential building around 30 something story. Okay, if you refer to Institute of Plumbing Design Guide, the ventilation pipe is half size of the drainage step. If the drainage step 150, the ventilation pipe, the secondary ventilation pipe in the standard talking about 75 mm. However, you go to the Hong Kong, a lot of building around 30 story, you can find that the ventilation pipe size is 150 at the same size with the drainage step. Okay, therefore the local engineer come from their practices. They got the experience of problem, learn from the error, have to increase. They have already increased the pipe size, not listed in the design standard. That's the reason why. Okay, go back to our position, our position nowadays. How we can decide that? Okay, no. Therefore, my logic is that once the pre-calculated insulation not work for that part, for ventilation part, we need to go back to our fundamental theory to consider the ventilation. Okay, we are not necessarily go to the very complicated fundamentals, just make it simple. Okay, therefore I would like to illustrate a case. Okay, now okay, I should draw in here. We have a water flow, okay, and create a pressure. The pressure could be positive, could be negative, but most likely will be negative. Okay, the negative pressure, the siphonage action, right? Therefore, we require the air in to fill up the partial vacuum so that the negative pressure will be mitigated. Okay, and this can be conducted via the experiment. And apart from there's also the misplace. Okay, Okay, for the fans, okay, here also change the direction. We will have the pressure variation, so we also need the ventilation, okay, at different location. Okay, this is a termination of ventilation pipe about the layout, some dimensional requirement for the pre-calculated system. Okay, this one is one I'd like to talking about. Once if the ventilation pre-calculated insulation insufficient, how we can apply a simple fundamentals to dealing with the problem? Only dealing with the ventilation pipe. I would like to call one experimental data which are applicable for our case. This experiment is was conducted in a section of pipe with annular flow of constant flow rate. And then they measure the air pressure at the two locations, okay, at a distance L. All right. So water flow rate is a QW, water flow, okay, and the corresponding air flow from the ventilation pipe is the air flow rate, y-axis, x-axis, okay, and there's a lot of curves. The experiment got repeated several times. They measure the delta P, the pressure differential between 2 points, and then divide it by the distance, L, and come up with so-called a pressure gradient, which is a Pascal per meter. Okay? Here is a family of curves or experimental results. Therefore, the experiment have been conducted 1,000 times, if not 10,000. Okay? So for the difference, the most interesting part is that the water flow rate across a range, there will be a local maximum air required in order to maintain certain pressure gradient. That phenomenon is important because in our application of drainage system, we do not know the actual flow rate at a certain moment. We're talking about the simultaneous flow rate, which is a maximum. Okay, and therefore we will have the flow rate in between somewhere else, but the phenomenon of air requirement is that there will be a maximum air required in order to maintain the pressure gradient of the pipework, so that we could make use of the data, the required air to limit the maximum pressure drop along the pipework. How this work? We get all this maximum point, okay, because across a wide range of flow rate, here is the maximum air required. Okay, I put it into the graph, okay, and generate an equation, okay, or you can read it directly from the graph, okay, which is the water this is the air should be the air flow rate required due to the maximum pressure gradient here. Okay, and then how this could be used? We could make use of our basic fluid mechanics, the Darcy formula, and the Colbert equation in order to calculate the flow rate. Okay, now apply those equations. Sometimes it needs some more calculation, but we get available for the chart information. Okay, put all the Darcy Colbert equation to have a graphical solution. Okay, this example I extracted from the ASHE, air conditioning. Okay, talking about the air pipe, air duct. Okay, now in the graphs shown here is this axis. We're talking about the air flow rate, and we also the pipe diameter here, and also the frictional loss, which is a pressure gradient. All right, so that we have the relationship over there. Now, what we need to do is that we need to maintain a suitable pressure gradient along the pipework. Our question is that if the ventilation pipe too long, okay, we need to increase the pipe size. Okay, so that increase the pipe size for the long air. Actually, we are going to maintain a certain pressure gradient. Okay, let me see if I included an example. Okay, here is an example. I think Forget that part first, okay? Only here. Now check for one ventilation pipe. For example, this ventilation pipe 100 meter. Because the ventilation have to go through the entire system, be ventilated at the rooftop. So that if the building is tall, okay, we need to run a long ventilation pipe. Suppose this example, 100 meter, not very long. And the ventilation pipe, we have already increased the pipe size, 150 mm, okay? And then the pressure gradient requirement is 375. Why this? Because the seal trap, the minimum water columning is 37.5 mm. Okay, there's a minimum. The pressure in order to penetrate it, overcome it, is 375. So then our design is from the atmospheric pressure to the point required ventilation, the maximum pressure drop not more than 375. Otherwise, the seal trap will be broken down. Okay. If our ventilation pipe is 100 meter long, therefore the corresponding pressure gradient will be 375 divided by the pipe length. This pipe length has to be the hydraulic distance. Hydraulic distance means at the flow passing through it, okay, the pressure created will be counted, including all the bands, also the fittings, okay? Correspondingly, if we have the pressure gradient, substitute into our equation or look at the graph, we will come up with the requirements of air. Okay, this requirement of air is the flow rate. With the flow rate, and the velocity, okay, we have a pipe diameter, we substitute into the Coburg equation, and then we calculate the friction factor. We substitute the friction factor into the Darcy equation, velocity known, density known. Here we can calculate pressure. So in this set of equation, we will check against if the pipe diameter, there's a hydraulic diameter, good for the pressure limit. If yes, it will be no problem. If not, we have to increase the size. Okay, my calculation in the illustrated example in the tutorial is around 380. I will consider this okay, just within the limits, error limit. Okay. Here, the slide, I do not show you in details the calculation step. I just leave it into a tutorial question. But in this few slide, my intention is that if for our context, the ventilation pipe most likely will be a problem. So need to take care about ventilation pipe. Is it necessary to go through that complicated calculation? The answer is no. All right. Here I quote another example, our sister city, Macau. I just finished with this few slides. I'll just leave it to go. The calculation, okay, I should join here. Which to show us LV is not a brand name, it's a vent pipe length. Okay, ventilation pipe up to 300 meter, Macau. Okay, and then the general stack diameter and vent pipe diameter. To store vent pipe diameter here, the general stack diameter there. Okay, just for example, 150 Jenks stack. Okay, for a 100 meter hydraulic diameter of the ventilation pipe, the required ventilation pipe size is 150 already, which is the same calculation result of the previous example. All right, so that are more or less okay. They are compatible. I didn't check the basis of this graph, but I think it's actually the same fluid mechanics. Okay, therefore I just assume they are compatible. So then we not necessary to go through complicated calculation. Still, some pre-calculated system for us. Okay, this is from the Macau standard, not from the Institute of Plumbing Design Guide, not from the British standard. Okay, therefore, my intention to show you various source of information is that I would like to equip you, all of us, okay, are able to apply any standard, and to understand what's the underlying assumption behind, so that we can apply those of the data correctly. All right, that's important. Okay, so here is the facts. Therefore, 150 drainage pipe size not necessary cut the half size for the ventilation pipe. Okay, do not go for it. Okay, another one. This is a practical example from the this is a public utilities board, which is a Singapore design. Singapore design, although it's Singapore got quite a lot of high-rise building, okay, similar to Hong Kong. Therefore, they have one design actually adopted in many buildings in Hong Kong, but not listed in any regulation because of performance-based setting for us, which also have the secondary ventilation. But the point is they got a special zoning. Here's a primary stack. We have a ventilation pipe here, but for the lowest floor, 2 floors, the discharge into a separate stack, and the stack will be extended to the roof again. Okay, and this extended part serves as a ventilation pipe for the higher zones stack. Therefore, still have two pipes, two vertical pipes. Okay, and these 2 pipes are used together, partially to serve as a ventilation, partially serve as a stack. It's different from any classification before we mentioned. All right, there's some sort of zoning. The lower zones separate stack, and this stack extended to the roof as well and serve as a ventilation pipe to the higher zones stack. Right? This is a special design. Okay, therefore here is the information I prepared for you. So in this lecture, do not expect they are the design procedure. No, I'm not talking about the design procedure. I try to address the basic fundamental and the principles behind those of the design tables. Therefore, I present it into another logic. Do not restrict yourself as a design procedure. Otherwise, you'll get confused easily. Okay, so that are my information. This is information prepared by me for this lecture. Hopefully, you can get benefits from it. All right, and maybe I just stop it here and leave you to digest all this information. Okay, and then see you next Tuesday. You remember, I would like to remind you again, we will postpone the next tutorial 2 weeks later. I will send you a separate email, okay, via the webboard. It will be a better arranged. Let us finish all the lecture before the tutorial. Okay? All right, just enjoy. Okay, we just stop it here. Thank you very much today. This is a busy day.